Okay, so just to recap here, if this criteria is met, where mu I is this and mu I hat is the fitted values, then the regression line y equal beta naught hat plus beta 1 hat x, that line is the least squares line. If we force beta 1 to be 0, then we only have the one parameter beta naught, and then it's only considering horizontal lines, and that works out to be y bar. We already worked out the solution, right? We want to, if you just want to minimize yi minus beta naught quantity squared, we've already worked out that solution in the previous lecture. But let's show it again, just to remind us. Well, I'm sorry, we worked it out in the previous lecture, but why don't we just show that that meets that criteria? Okay, so here's the criteria that we said has to be equal to 0 to get the regression line. Let's plug in our beta naught hat. So here we've converted, in this case, mu I hat to beta naught hat and mu I to just beta naught. And this term doesn't depend on I, so we can pull it out of the sum. And we get this sum right here. And that will equal 0, just expanding it out, if ny bar minus n beta naught equals 0 right there, and then solve that for beta naught hat, you get beta naught hat equals y bar. So exactly like we did it previously, when we previously developed these same equations, only now we've kind of created a somewhat automated way of doing it. We just have to figure out, parameterize our mean mu I hat, and then show that equation equals 0, and then we've got it. So it gives us more of a constructive way to do it rather than before when we had a sort of trick. Okay, so now let's do regression through the origin. Okay, so here, remember, we need to have this equation be equal to 0, and where mu I is this and mu I hat is that, and then this guy will be the regression line. If now, instead of forcing beta 1 to be 0, if we force beta naught to be 0, right, then we will have a regression line through the origin. Okay? And in this case, the solution works out to be beta 1 hat is the inner product of y and x divided by the inner product of x by itself. If you're used to that sort of notation, but it works out to be that. And it'll make a little bit more sense when we include an origin. Okay, but let's just show that this works out to be the case. Okay, here's the criteria that we have to meet. I want my pen, not the square. I get it. There we go. There's a pen. This is the criteria that we need to be 0, and here we've parameterized mu I to be equal to beta 1 xi. Okay, so plugging in our beta 1 xi and mu I hat as beta 1 xi hat, so we get this equation right here, just plugging in. Then factoring out the xi, right? We can factor out an xi here. Okay, there we've factored out an xi. Then we have a beta 1 hat minus beta 1, and that can get pulled out of the sum, and the xi can get brought into that sum, so we wind up with this equation right here. So this, if that equals 0, then this will equal 0, okay? And so this will equal 0 if that equals 0. Expanding it out and solving yields the equation that we said was right.